Welcome to Study Loop.
For this problem, on the topic of electric potential, we are told that two protons are released when they are nearby at 0.75 nanometers apart, and we want to calculate the maximum speed they will reach as well as the maximum acceleration. We also want to know at what point they will reach this maximum speed as well as the maximum acceleration. Now, we know that they will have maximum speed when they are very far apart, and all their initial electric potential energy has been converted to kinetic energy. So if we let point A be the point at which they are 0.7 nanometers apart, and point B be the point when they are very far apart, we can apply the conservation of energy. And their initial kinetic energy plus their initial potential energy must equal the final kinetic energy plus the final potential energy when they are very far apart. So Ka plus Ua must equal to Kb plus Ub. Now Ka is equal to 0 and Ub is equal to 0. When they are far apart, there's no potential energy between them, and initially there's no kinetic energy since they are both at rest. So we get that the final kinetic energy Kb is equal to their initial kinetic energy Ua. And we know the kinetic energy between, or the potential energy rather, between the two protons is K times E squared over Ra. Remember, they gain the kinetic energy since they repel each other due to both having positive charges. And this is equal to the constant K, which is 8.99 times 10 to the 9 Newton meter squared per Coulomb squared times the charge on the proton, 1.6 times 10 to the minus 19 coulombs squared, divided by the separation between them initially, which is 0.75 nanometers, or 0.75 times 10 to the minus 9 meters. Calculating, we get the kinetic energy, the final kinetic energy, to be 3.07 times 10 to the minus 19 joules. So this is the maximum kinetic energy that the protons can have. And so from here we can calculate the speed with which they move off. So the kinetic energy K is equal to a half mvv squared, the speed of one proton, vb, plus a half mvv squared, the speed where vb is the speed of either of the protons at a distance far away from their starting point. So kb is actually equal to mvb squared. So these are the contributions from each proton. So then we can rearrange this equation and solve for their velocity, for their speed at this point. And this is the square root of the kinetic energy K divided by the mass of the proton m. And we already calculated the kinetic energy, so we can substitute this in. That's 3.07 times 10 to the minus 19 joules for each proton divided by a mass of 1.67 times 10 to the minus 27 kg. And so calculating, we get the maximum speed that each proton will reach to be 1.36 times 10 to the 4 meters per second. And remember, this is the speed at their furthest distance apart at point B. Now we want to calculate the magnitude of their maximum acceleration. Now the acceleration is largest when the force between them is the largest, and that's due to Newton's second law. And so this occurs when their separation is 0.75 nanometers, their closest distance. And the force between them, F, is equal to the constant k times e squared over the square of the separation r squared. And if we calculate this, we can put in our values. That's 8.99 times 10 to the 9 Newton meter squared per coulomb squared times 1.6 times 10 to the minus 19, and that's coulombs, divided by the separation of 0.75 times 10 to the minus 9 meters, and all of this is squared. Calculating, we get the maximum force between the two protons to be 4.09 times 10 to the minus 10 newtons. And from Newton's second law, we know the acceleration A is equal to the resultant force divided by the mass. And so the acceleration of each proton is the force on each proton, 4.09 times 10 to the minus 10 newtons over the mass of each proton, 1.67 times 10 to the minus 27 kg, which gives us the maximum acceleration when the two protons are at their closest approach of 2.45 times 10 to the power 17 meters per square second.